Why is gravity so much weaker than the other fundamental forces of nature? This question leads us to some of the deepest mysteries in theoretical physics. Gravity and electromagnetism both produce forces between particles, but their strengths differ by an astronomical factor. Let us begin by quantifying just how weak gravity really is compared to electromagnetism. Consider two protons separated by 1 meter. We can calculate both the gravitational and electromagnetic forces between them. The gravitational force is given by Newton's law, g times the product of masses divided by distance squared. The electromagnetic force is given by Coulomb's law, k times the square of the elementary charge divided by distance squared. Taking the ratio, we find that the electromagnetic force is about 10 to the 36 times stronger than gravity. This is an enormous hierarchy. Even more dramatically, for an electron and proton in a hydrogen atom, the electromagnetic attraction is still 10 to the 39th times stronger than gravity. This ratio is approximately 10 to the 39th, showing that gravity is utterly negligible at atomic scales. This diagram shows the relative strengths. The electromagnetic force bar would need to be billions of times larger than this screen to be shown to scale. Pause and think. If gravity is so incredibly weak, why do we notice it at all in everyday life? The answer is that gravity is always attractive and acts on all mass. Electromagnetic forces cancel out in bulk matter because of charge neutrality, but gravitational effects always add up. To understand this hierarchy more deeply, we need to work in natural units where fundamental constants take on simple values. In natural units, we set Planck's constant and the speed of light equal to 1. This simplifies our equations significantly. The fine structure constant alpha, which measures electromagnetic strength, is about 1 over 137. This is a dimensionless number. The gravitational coupling constant for protons is g times the proton mass squared, which is about 10 to the minus 38. This is remarkably small. The extreme weakness of gravity is encoded in this extraordinarily small dimensionless coupling constant. The natural scale for quantum gravity is set by the Planck scale, where gravitational and quantum effects become comparable. The Planck mass is defined as the square root of Planck constant times c divided by Newton's constant. Numerically, the Planck mass is about 1.22 times 10 to the 19 giga-electron-volts. This is enormous on particle physics scales. The Planck length, the corresponding length scale, is about 10 to the minus 35 meters, incredibly tiny. This logarithmic scale shows the enormous gap between the electroweak scale at 10 to the 2 giga-electron-volts and the Planck scale at 10 to the 19. The hierarchy problem asks why the electroweak scale is so much smaller than the Planck scale. This seems unnatural from a quantum field theory perspective. In quantum field theory, particle masses receive quantum corrections from virtual particle loops. These corrections are sensitive to the highest energy scales in the theory. The Higgs mass squared receives corrections proportional to the cutoff scale lambda squared. If lambda is the Planck scale, this correction is huge. If the cutoff is the Planck scale, the correction to the Higgs mass squared is of order Planck mass squared, which is enormous. To get the observed Higgs mass of 125 giga-electron-volts requires canceling these corrections to 1 part in 10 to the 32. This seems incredibly unnatural. Virtual particle loops contribute enormous corrections to the Higgs mass, making the hierarchy problem a central puzzle in particle physics. Pause and think. Could it be that gravity is simply fundamentally weak, with no deeper explanation required? This is possible in principle, but the problem is that quantum corrections want to pull masses up to the highest scale in the theory. Keeping gravity weak requires extreme fine-tuning at every order in perturbation theory. One proposed solution involves extra-spatial dimensions. If gravity can spread into extra dimensions while other forces cannot, gravity appears weaker in our three-dimensional world. The ADD model, named after Arkani Hamed, Dimopoulos, and Diwali, proposes large, flat extra dimensions. In this model, the true fundamental Planck scale m star can be much lower. The observed four-dimensional Planck scale is related by m Planck squared equals m star to the 2 plus n times r to the n, where n is the number of extra dimensions and r is their size. The key idea is that gravity spreads into n extra spatial dimensions, each of size r, while electromagnetic and other standard model forces remain confined to our three-dimensional brane. We can solve for the size r of the extra dimensions. It goes as the Planck scale over m star to the 2 over n times 1 over m star. If we want m star to be around 1 tera-electron volt, the weak scale, and we have 2 extra dimensions, then r works out to be about 1 millimeter. This is macroscopic. This shows our three-dimensional brane as a flat sheet. Gravitational field lines leak into the extra-dimensional bulk, diluting gravity's strength in our world. For one extra dimension, r would need to be about the size of the solar system, which is clearly ruled out. For more than 2 dimensions, r becomes submillimeter. These scenarios can be tested with short-range gravity experiments that look for deviations from Newton's law at millimeter and submillimeter scales. An alternative approach uses warped extra dimensions, where the geometry of space-time itself explains the hierarchy. The Randall-Sundrum model introduces one warped extra dimension, where the metric has an exponential warp factor. The 5-dimensional metric has an exponential warp factor, e to the minus 2 krc phi, where k is the curvature scale, rc is the compactification radius, and phi is the extra-dimensional coordinate. There are 2 3-branes, a Planck brane where gravity is localized, and a TIV brane where standard model fields live. The warped geometry exponentially suppresses mass scales. A mass parameter on the Planck brane appears exponentially suppressed when viewed from the TeV brane. M weak is approximately m Planck times e to the minus krc pi. With krc of order 10, the exponential warp factor easily generates the hierarchy between the Planck and weak scales without fine-tuning. The vertical lines represent mass scales at different points in the extra dimension. The warped geometry causes masses to be exponentially redshifted from the Planck brane to the TeV brane. Pause and think, how do particles actually propagate through this warped geometry, and why does this affect their masses? Each particle has a wave function profile in the extra dimension. The overlap of these profiles with the TeV brane determines the effective masses and couplings we observe. Particles localized near different branes experience different scales. If the fundamental gravity scale is near the weak scale, this has dramatic experimental consequences. One striking prediction is that microscopic black holes could be produced at particle colliders like the Large Hadron Collider if the gravity scale is truly at the tera-electron volt range. The minimum black hole mass would be around m star, approximately 1 tera-electron volt, making them accessible to LHC energies. Gravitational waves would show modified behavior at high frequencies, potentially detectable by future high-frequency gravitational wave observatories. Current experimental searches have found no evidence for extra dimensions or weak-scale gravity. This places strong constraints on the size and number of extra dimensions. A microscopic black hole produced at a collider would immediately evaporate via Hawking radiation, producing a distinctive signature of many energetic particles. These ideas connect naturally to string theory, where extra dimensions are a fundamental feature. String theory naturally predicts 10 or 11 spacetime dimensions. 6 or 7 must be compactified to match our observed 4-dimensional world. In string theory, branes are extended objects where open strings can end. Our universe could be a 3-brane embedded in higher dimensional space. The string scale ms is 1 over the square root of alpha prime, the fundamental string length parameter. This could be much lower than the Planck scale. The string landscape contains an enormous number of possible compactifications, each giving different low-energy physics. Finding our universe in this landscape remains a major challenge. Let us review the current experimental constraints on these scenarios. Torsion balance experiments test Newton's law at submillimeter scales, constraining large extra dimensions with n equals 2 or 3. The Large Hadron Collider has searched extensively for signatures of extra dimensions and microscopic black holes, finding no evidence up to several tera-electron volts. Precision electroweak measurements constrain Kaluza-Klein resonances, which are excitations of standard model fields into extra dimensions. Current constraints typically require the fundamental scale m star to be greater than about 5 tera-electron volts for large extra dimensions. This bar chart represents how experimental constraints have progressively tightened over time, pushing the allowed parameter space to higher energies. Pause and think. Is it possible that extra dimensions exist but are fundamentally undetectable by any experiment? Extra dimensions, much smaller than current experimental resolution, remain possible. However, if they are much smaller than the weak scale, they do not solve the hierarchy problem, so we lose the primary motivation for considering them. Several alternative approaches to the hierarchy problem exist beyond extra dimensions. Supersymmetry proposes that every particle has a superpartner with opposite spin statistics. Quantum corrections from bosons and fermions cancel, stabilizing the hierarchy. Composite Higgs models propose that the Higgs is not fundamental, but a bound state of more fundamental constituents, similar to pions in QCD. Anthropic reasoning suggests that fundamental constants vary across a multiverse, and we observe values compatible with our existence. This is controversial and philosophically challenging. The tension between naturalness, the idea that parameters should not require special values, and fine-tuning, which means they do, remains unresolved. Let us summarize what we have learned about the hierarchy problem and possible solutions involving extra dimensions. We established that gravity is approximately 10 to the 36 orders of magnitude weaker than electromagnetism for comparable particles. The enormous gap between the electroweak scale at 10 to the 2 gigaelectronvolts and the Planck scale at 10 to the 19 gigaelectronvolts appears unnatural given quantum corrections. Extraspatial dimensions provide a mechanism to lower the fundamental gravity scale while keeping it apparently weak in 4 dimensions through geometric dilution. Large, flat extra dimensions dilute gravity through volume, while warped extra dimensions use exponential geometry to generate the hierarchy naturally. Current experiments have constrained the parameter space significantly, but have not ruled out extra dimensions entirely. The allowed regions are being systematically explored. The hierarchy problem has motivated numerous theoretical approaches. Extra dimensions are one possibility among several, each with unique predictions and challenges. Future collider experiments, if built, will probe energy scales above 10 tera-electronvolts, potentially discovering new physics that addresses the hierarchy problem. Gravitational wave astronomy provides an entirely new way to test theories of gravity at previously inaccessible scales and energies. Despite decades of theoretical and experimental work, why gravity is so much weaker than other forces remains one of the deepest unsolved puzzles in fundamental physics.